Hello guys, welcome back to another video on my channel Gamma Die Gamma. In the last video, we completed our exploration of the double integral from the Romanian mathematical magazine, where we used predominantly the identity we proved in the video before that. So in this video, in the spirit of adding more weapons to our integral arsenal, which is already quite vast, I thought of including another nice identity or another nice formula, the Lobachevsky's Dirichlet integral formula. So let's see what that is. Let's get started. So the theorem is, if we have a function f going from reals to reals satisfying f of x equals f of pi plus x equals f of pi minus x. So this sort of pi periodicity here for all x belonging to R, and it is Riemann integrable on the interval 0 pi over 2 both inclusive, then we have integral from 0 to infinity sine of x over x times f of x dx is just integral 0 to pi over 2 of f of x dx. So essentially we can change our bounds from 0 to pi over 2 and essentially forget about the sine of x over x part, is what the formula tells us, assuming we have the conditions satisfied. So the proof of this, and this will be a little analysis heavy, but always when it gets dry, remember what's at stake. This nice formula, which is waiting to be added to our armory, our arsenal. So the proof begins by writing integral 0 to infinity sine of x over x f of x dx as a discretized sum. So we're going to split our interval from 0 to pi, pi to 2 pi. So we're going to make segments of length pi and add them together infinite number of times. So we're breaking our 0 to infinity between segments of k pi and k plus 1 pi, where k is going from 0 to infinity. So we have to add all of them up because the original sum integral was from 0 to infinity. We can segment up our interval. So we have sum from k equals 0 to infinity, integral k pi to k plus 1 pi, where we're making segments, infinite segments of length pi, sine of x over f of x dx. The use of such discretization will become useful in a short while, and if you remember, this is actually a similar kind of approach that we did for evaluating an integral which had, say, a fractional part. So we can rewrite this into two sums again. So sum from k equals 0 to infinity, integral k pi to k plus 1 half pi, sine of x over x, f of x dx, plus sum from k equals 0 to infinity, integral k plus 1 half pi to k plus 1 pi, sine of x over f of x dx. So what I've done is I've split this interval of length pi into half essentially. So the first goes from k pi to k plus 1 half pi, and the other goes from k plus 1 half pi to k plus 1 pi. The use of this is for the second integral here. Let's change k to k minus 1. So now the first is as it is. The second actually now runs from sum from k equals 1 to infinity, and the bounds have changed. So we have k minus 1 half times pi and k pi. Sine of x over f of x dx is all the same. Now we have to do the substitution. X goes to x plus k pi for this first integral, and x goes to k pi minus x for the second one. Upon doing this substitution, we have sum from 0 to infinity, integral 0 to pi over 2 sine x plus k pi over x plus k pi, f of x plus k pi dx, plus sum from k equals 1 to infinity, integral 0 to pi over 2 sine of x minus k pi over x minus k pi, f of k pi minus x dx, where we've appropriately changed the bounds of integration based on our substitution. This is simple U substitution stuff. So notice when we expand sine of x plus k pi, we can use the compound angle formula for the sine to get sine of x times cosine k pi. Cosine k pi is minus 1 to the k. So we have everything else is the same, minus 1 to the k sine of x over x plus k pi. And using the periodicity condition of f, we just have f of x again dx. Similarly, in the second integral, everything else is the same. We again have a minus 1 to the k factor sine of x over x minus k pi, and similarly with periodicity f of x dx. And all of this can be written as the zeroth term. We want to get a common summation here in both these terms. So the common term is start from k equals 1. So we have to account for this zeroth term here, k equals 0 term, which happens to be integral 0 to pi over 2 sine of x over f of x dx. That's the zeroth term. And then for the k equals 1, we can combine both these uh, terms in the integral. So we have sum from k equals 1 to infinity, integral 0 to pi over 2 minus 1 to the k, which is common, 1 over x minus k pi plus 1 over x plus k pi, and then sine of f of x is common, dx. We can combine both of these again further and also take the sum in, but when we do that, we'll have to consider that we had a limit. We had to take a partial sum from k equals 1 to n, and then take the limit as n goes to infinity. We still cannot justify putting this limit inside the integral, although we have been doing in the past, being hand wavy, we've not been as rigorous, but in this video I will try to be more rigorous. So we have the limit as n goes to infinity, and we just have a partial sum, because we still have to argue if we can take the limit inside, which I will do later in the video. So limit n goes to infinity, integral 0 to pi over 2, 1 over x from the k equals 0 term, plus sum from k equals 1 to n, minus 1 to the k, 1 over x minus k pi plus 1 over x plus k pi, sine of x f of x dx. That everything else is the same. And we can write this term in the big parentheses as un of x. And the rest is sine of x, f of x dx, and integral from 0 to pi over 2. And we are obviously taking limit as n goes to infinity. Now, to evaluate this un of x, which is just 1 over x plus sum from k equals 1 to n minus 1 to the k, 1 over x minus k pi plus 1 over x plus k pi, can be compactly written in this nice form. Sum from k equals minus n to n minus 1 to the k over x plus k pi, because we notice that this will indeed be the same form. If we split this from minus n to 0 and 1 to n, this will indeed give us back the form we had on top. So this is a nice compact form for un of x. Now to evaluate un of x, this is kind of a brilliant observation. Take alpha to be between a minus pi to pi inclusive, y belongs to reals, and consider the Fourier series of cosine y alpha. So cosine y alpha, in terms of a classic Fourier series expansion, is given by a naught over 2, the constant term, plus sum from k equals 1 to infinity, a sub k cosine k alpha plus b sub k sine of k alpha. Notice cosine y alpha is actually even, so the bk term, without doing any integration to solve for bk, we can just evaluate and find that to be 0, because cosine y alpha is even for all k greater than or equal to 1. So a naught has a formula, is 2 over pi integral 0 to pi cosine y alpha d alpha. That is going to give us 2 times sine pi y over pi y. And ak similarly has the formula 2 over pi integral 0 to pi cosine y alpha cosine k alpha d alpha, which we can actually evaluate nicely using a product to sum formula. So we have 1 over pi integral 0 to pi cosine y plus k alpha plus cosine y minus k alpha d alpha, which is simple to evaluate, which is 1 over pi sine of y plus k alpha over y plus k plus sine of y minus k alpha over y minus k, evaluated from 0 to pi. And simplifying everything using compound angle formula at places, we get minus 1 to the k sine of pi y over pi, 1 over y plus k plus 1 over y minus k for, k greater than or equal to 1. That was the condition on the ak. Okay, that's nice. Now, since alpha is between minus pi to pi, we can readily make the choice of alpha equals 0. When I do that, I'll have cosine of 0, which is 1, on the left hand side here. We know what a naught is and we know what ak is now, so we can just plug those in for alpha equals 0. We get 1 equals sine of pi y over pi y plus sum k equals 1 to infinity minus 1 to the k sine pi y over pi 1 over y plus k plus 1 over y minus k. So we have 1 equals sine pi y, and sum from k equals minus infinity to infinity. We can club both these terms in this compact way. Minus 1 to the k over pi y plus k pi. We can combine this term with this infinite sum, just like we did with the un, to get this nice form, which we actually recall is indeed, so sine pi y is the external factor. Limit n goes to infinity un of pi y, which you can recall indeed fits the nice form that we had for the un. But x is just pi y now. So then, of course, taking pi y to be x for all x belonging to 0, pi over 2 exclusive, we get that limit n goes to infinity un of x, comparing left hand and right hand side, is just cosecant of x, right? Because we divide by the sign to get rid of this coefficient. So that means our problem of this integral from 0 to infinity sine of x over x f of x dx has just simply become to evaluate limit n goes to infinity of 0 to pi over 2 integral un of x sine of x f of x dx. And of course, if we can just take the limit inside, if only we could take the limit inside, we'd have we have limit as n goes to infinity of un of x, which we indeed know is cosecant of x. That cosecant will kill the sign, and we'd just be left with integral 0 to pi over 2 f of x dx, and that would be it. That would solve that would prove the theorem that we had. So to move the limit inside, we need something that's known as the dominated convergence theorem in analysis, DCT, for which we need to have un of x sine of x f of x, which is the integrand here, is less than or equal to capital M of x for all n, and x belonging to 0, pi over 2 exclusive, where m is a Riemann integrable function. Now we know that the sine of x is bounded, and f of x is Riemann integrable on the interval 0 to pi over 2 inclusive. From that's the domain they gave us at the beginning in the theorem assumptions. So it must be bounded as well. This is a standard result from Riemann integrability, that if a function is Riemann integrable on a compact interval, then it must be bounded. So all that's left to be shown to satisfy the condition for which we can use the dominated convergence theorem is to have un of x be bounded by some m of x, because we know sine and f of x are bounded. So we just need to show that un of x is bounded, and then we can use dominated convergence theorem and justify moving this limit inside. I hope that this line of thought is clear. This is something we often do in analysis. So now to show that this un, which is actually an alternating series, if you think in terms of the partial sums, sorry, I have to keep going up for the real form of un. So this is an alternating series. Un becomes the n becomes a label of a sequence, so it becomes a sequence of partial sums, essentially, which have this alternating uh, sum going on. For that, we can use the alternating series estimation theorem, which says that if we have Sn in the limit as n goes to infinity, so Sn is some partial sum from k equals 1 to n minus 1 to the k minus 1 bk. So it's an alternating partial sum. So the limit as as n goes to infinity, suppose that converges and it has some value s. Then satisfying two conditions, that bn plus 1 is less than bn, is decreasing in the bn coefficients for all n, and limit n goes to infinity bn is 0, then absolute value s minus Sn, or the difference between the limit and the nth partial sum in absolute value is less than or equal to bn plus 1, which is the coefficient, the non-alternating coefficient or summand at evaluated n plus 1. This is the theorem. This is what they've given us. You can prove this. Is not that hard to prove, but that we're not going to do this in that video. So for us, in our case, bk is going to be, if we go back to the big expansion of u, is going to be this term and this term, because the way we define, we're going to use the estimation theorem. We have sum from 1 to n, just like we had in the statement of that theorem, 1 to n. So we're going to consider two bk's. One is 1 over x plus k pi, and the other is 1 over x minus k pi. We can check easily that they satisfy these assumptions, conditions 1 and conditions 2. And then we can just use this upper bound. So we have sum from k equals 1 to infinity minus 1 to the k over x plus k pi minus sum k equals 1 to n minus 1 to the k over x plus k pi in absolute value. So the difference between the limit, which is at infinity, minus the nth partial sum, which you can also evaluate, it is actually sum from k greater than n minus 1 to the k over x plus k pi absolute value, is less than or equal to, according to this, absolute value 1 over x plus 1 plus n times pi, because we had a n plus 1 here, which you can see is less than or equal to 1 over n pi. Similarly, for the other 1 over x minus k pi term, we get a similar bound, that sum from k greater than n minus 1 to the k over x minus k pi less than or equal to 1 over x minus 1 plus n times pi, which is less than or equal to 1 over n pi. So we have the same upper bound for both of them. And with that upper bound, we can see that the partial sum k equals 1 to n minus 1 to the k over x plus or minus k pi is less than or equal to the limit value at infinity. So sum k equals 1 to infinity minus 1 to the k over x plus or minus k pi plus 1 over n pi, because this is just an upper bound. So you remove the absolute value and you just consider the upper bound, and you get this just by moving this on the, adding this on the other side when we remove the absolute value. So now un, which was 1 over x plus sum k equals 1 to n minus 1 to the k, 1 over x minus k pi plus 1 over x plus k pi, that if we consider absolute value of un of x, we get absolute value of all those things. But we know what upper bound on each of them are. Okay, so what's happening here, it's a little obscure. I skipped one step actually. Is I'm going to use the upper bound that we got here on each of these individually. So we get, we can replace this n with an infinity and add a 1 over n pi for each of these. So that gives a 2 over n pi, and each of those things that we added at infinity plus the 1 over x will actually give us limit as n goes to infinity of un of x, essentially. And all this is, under the absolute value, but it's all positive, so we can just remove that. That equals 2 over n pi, and we know what the limit of un of x is just cosecant of x. So if we consider un of x times sine of x in absolute value, that's less than or equal to 2 over n pi absolute value sine of x plus 1. But we know the sine of x is bounded by 1, upper bounded by 1. we get less than or equal to 2 over n pi plus 1, which we know is less than or equal to 2 because simple estimations. So we have indeed found, instead of finding a function which is Riemann integral, which is an upper bound, we found a constant. So it's a constant function, and a constant is Riemann integrable on 0 to pi over 2. So we've indeed satisfied the criteria for the dominated convergence theorem, and we can happily move this limit inside this integral to get integral 0 to pi over 2 limit n goes to infinity un of x sine of x f of x dx. We know what the limit of un is. Integral 0 to pi over 2 cosecant x sine x f of x dx. The sine and cosecant are reciprocal of each other. They will evaluate to 1 in a product. So we have integral 0 to pi over 2 f of x dx. And that's it. That's how you prove it. This is how analysis is done. If you don't know what analysis or real analysis or any of that rigorous kind of stuff is. Now, this is a very, very powerful result. The only criteria, only condition to use this is f must be periodic and Riemann integrable. You can make this a little more general by considering a Lebesgue integral, but I don't think that is really necessary for the confines of this channel. There's another result where instead of having, so these two are equal, but instead of having equal to f of x, we have minus f of x. So it's not really odd, it's just sort of anti-periodic. So in that case, instead of a sine, we have just a cosine. We have cosine of x over x essentially when that happens. So yeah, that's just a variation of that. It's less well known. This is the more common result we would see everywhere, and I will do some nice examples where we really need this result in the next couple of videos. So stay tuned for that, and thanks for watching. Peace out, and keep doing that.